Today I would like to begin discussing a very major application of plasma physics, that is thermonuclear fusion. In this we will discuss basic fusion reactions, primarily the deuterium-tritium reaction that is used to produce energy, and we will discuss Lawson criterion for energy break even, and then we will discuss two approaches to fusion. One is called magnetic fusion and second one is called inertial confinement fusion, also known as laser driven fusion. And then we will begin discussing some basics of toroidal plasma confinement, which is at the forefront of fusion research, a device called Tokamak. Let me begin with the basic equation. Deuterium and tritium are considered to be the major source of or major thermonuclear fuel. If they can be fused, the nuclei of deuterium and tritium, they can be fused, then they will produce a helium nucleus called alpha particle with atomic number 2 and atomic weight 4. Deuterium has atomic number 1, atomic weight 2. Tritium has 1 and mass number is 3. Deuterium and tritium are isotopes of hydrogen. If they can fuse, the nucleus can fuse with each other, then they can produce a helium nucleus plus a neutron which has 0 charge but mass number is unity, and in this process 17.6 MeV of energy is released. The energy that goes to alpha particle is 3.5 MeV, and the energy that goes to the neutron is more, 14.1 MeV. Well, deuterium and tritium are isotopes of hydrogen. Deuterium could be recovered from seawater at reasonable cost, and tritium can be recovered from lithium, which is quite in abundance in the soil, and about 7% of lithium is 3Li6. If you bombard this with a neutron, then this will produce a alpha particle, 2He4, and tritium nucleus, which is 1T3. In the process, 4.8 MeV energy is released, and very significant amount of seawater is deuterium. Normally water is H2O, but typically around 0.1% or slightly less than that of seawater is D2O. So deuterium is available in seawater and one can recover it at not too high a cost. The problem is that if you want to undertake this reaction, then the fusion has to, the nuclei have to overcome a very strong repulsive force between the two, because both are positively charged. This has a proton in the nucleus, this also has a proton. When they come very close to each other, they repel via Coulomb force. So they have to be brought in within the range of nuclear force so that they could fuse. For that, the temperatures that are needed are typically of the order of 10 to the power 8 degrees Kelvin, so that the nuclei could cross the Coulomb barrier and confuse. An important quantity of consideration is called fusion cross-section, which depends strongly on the energy. So if I plot here a graph, fusion energy as a function, sorry, the fusion cross-section, this is I am plotting in per meter cube in meter square, and I plot energy of deuterium when it is bombarding or coming close to the tritium, and this I write in keV. Then suppose it is 10 here, this is 100 here, and this is 1000 here. This is logarithmic scale. And the fusion cross section, if I write here 10 to minus 32 meter square, and let me write 10 to the power minus 30 here, and let me write 10 to minus 28 here. Fusion cross section below 10 keV energy is small. So it begins from here, it peaks around 100, typically like this. The curve goes like this and then falls off, something like this. So what is required is that you must have enough kinetic energy of tritium nucleus, maybe 10 keV or higher, so that the fusion cross section is substantial. Even if the plasma temperature is 10 keV, in the Maxwellian tail, if I plot the distribution function, energy distribution function f of electrons as a function of energy, then this goes like this. So there are substantial number of atoms or ions in the Maxwellian tail. So even if the average energy at which f peaks could be around 10 keV, the number of ions with 20 or 30 keV energy are also quite very substantial, and then they can cause thermonuclear fusion. But 10 keV certainly is some sort of a guideline that one should aim to achieve. So people have focused their attention in achieving plasma temperatures of about 10 keV, and please remember 1 keV corresponds to about 10,000 degrees Kelvin, and hence 10 keV temperature is around 10 to the power 8 degree Kelvin, 10 crore degree Kelvin, which is a huge temperature. No container can sustain such high temperatures, and hence one should worry about the confinement of such a hot plasma. All state of matter is in the plasma state at such high temperatures. So primarily we are dealing with a deuterium tritium plasma undergoing thermonuclear reactions of deuterium and tritium and producing alpha particles and neutrons via the reactions. Well, two things are important in here. Number one, that one should be able to heat this mixture to such a high temperature. This is the first requirement. And second thing is that once the mixture has reached the temperature of 10 keV or so, and fusion reactions have started taking place, then the alpha particles that are produced in the reaction, they should be trapped within the plasma and they should be able to heat the plasma or sustain the heating, sustain the temperature. That is called ignition. So two important considerations are that one should achieve break even, means the nuclear energy produced via DT reactions should exceed the amount of energy that you have put in to heat the plasma, and secondly the alpha particles that you produce should be able to sustain that temperature. Now let me make some estimate of energy equilibration or energy equality, that I want that the energy output to be equal or greater than energy in. If Win is the energy input to heat the plasma and this is the energy output. Energy input you can certainly think in terms of particle density etc. and temperature. If your system has, suppose, electron density as n, obviously deuterium density would be half of it, because half the electrons are released from by deuterium and half are released by the tritium. So, this will be n by 2. Tritium density I can take to be n by 2 also, and temperature of, suppose, these 3 species, they may differ, but suppose typical temperature I choose to be equal to T, and the volume of the plasma, suppose V. So, the total number of particles in the system are NV, and the kinetic energy of every particle, if I assume them to be a Maxwellian, having Maxwellian distribution function, is 3 by 2 into T, where Boltzmann constant is hidden here, but this is the number of electrons. If you count the total number of particles, electrons plus deuterium ions plus tritium ions, then this becomes 2n. So, this is the right equation. So, total energy input that you have to provide to initiate the process is so much, where T has to exceed 10 keV. Now, let us see how much energy one can produce. If the confinement time of the system is tau, suppose this mixture stands there for a duration of the order of tau. Let me estimate that. The number of fusion reactions a particle will go, say deuterium will undergo with tritium, is defined as, I will call this nu f, which is equal to the number of tritium ions per unit volume into fusion cross section into velocity of deuterium, thermal velocity of deuterium. Collision frequency normally is a product of density, collision cross section into thermal velocity. This is the kind of thing. And in each reaction you are producing energy, say EF. So, let me call EF as the fusion energy per reaction, which is 17.6 MeV. Fusion energy produced per reaction. Nu f is the fusion collisions each deuterium ion is undergoing with the tritium ion. So, now to calculate the energy output W out, this should be equal to total number of fusion reactions. Now, in a unit volume, the number of tritium ions is Nd, they go nu f, each of them undergoes nu f collision per second, fusion cross section collision per second, and in the process produces so much energy. So, this is the amount of fusion energy produced per unit volume multiplied by the volume, is the total energy output. If I put Nd is equal to n by 2, where n is the electron density and Nt also is n by 2, then this can be written as n square by 4, n by 2 from here, n by 2 from there, multiplied by sigma f into Vd into Ef into V, and I want this to exceed the energy that you have put in, which is equal to NV into 3 times T. Please remember, sigma F is a very strong function of energy, and Vd also depends on temperature. It goes as under root of temperature. So these equality, if I put, and please, I made a mistake here. This W out is the amount of energy produced per second. If the confinement time of the system is tau, energy confinement time, I may call it tau E. Then I must multiply tau here also. So this gives me, one n will cancel out, a product of density of electrons into energy confinement time of the plasma. This should satisfy certain inequality. And if I take the equal sign here, then this is called the Lawson criteria. And when you put these numbers here, what you find is that density and energy confinement time product must exceed or should be of the order of 10 to the power 14 per centimeter cube into second at an electron temperature of or plasma temperature of 10 keV. At other temperatures this number will be different. But primary goal of fusion research in last 30-40 years has been to achieve plasma density into confinement time product satisfying this condition. Well, as far as ignition is concerned, if you want to have the burn continue by extracting energy from the alpha particles, what you require, that whatever energy is produced, W out that you call, sorry, let me reframe this. What I want is that the energy produced in alpha particles per second, this must be equal or bigger than the energy lost via radiation or other processes. If the plasma energy that we call as energy N, which was 3 N T into V, where V is the plasma volume, N is the density of the electrons in the plasma, and T is the plasma temperature. This is the energy that is at any instant of time contained in the plasma particles. If the plasma confinement time is tau E, so that in that much time so much energy is lost. So let me define the energy confinement time as tau E. Then this is the energy lost per second, typically this is the estimate, and energy produced per second will be how much? I just estimated this quantity. So that quantity was W out is the total energy produced in alpha particles plus neutrons, 17.6 MeV Wf. If I divide this by, multiply by this by factor of energy of a alpha particle divided by, rather let me put some symbol here, E alpha upon energy released in a fusion reaction. This is 17.6 MeV and alpha particle is 3.5 MeV. So this quantity is like 1/5. So this, if this exceeds this number, then we say that we have achieved ignition. and you do not require any more heating mechanism. But this factor energy released per nuclear fusion reaction is E alpha for the alpha particle, and total energy released is EF, which is like 17.6 MeV. So this ratio is 1/5. So what you require is this. But first generation experiments on fusion focused on achieving Lawson criterion. This requires higher value of n tau product. Now there are two schemes to achieve this product. One is called magnetic fusion, where you employ magnetic field to confine particles. We have already seen that if you have straight lines of force like the magnetic lines of force, then the charged particles, maybe electrons, if they move, they are introduced in the system, they will be confined across the line of force, though they are free to move along the lines of force. So there is a confinement in two transverse dimensions, but there is no confinement if the lines of force are straightforward in this direction along the length of the lines of force. Then we came across the mirror confinement, that even if the lines of force are straightforward, but if you can create a lines of force like this, that they converge like in a mirror machine, then the electrons and ions which are gyrating over the field lines here, when they come close to the throat, and if they have large pitch angle, they can come back and they will be confined in the system. So magnetic field can provide confinement in 3 dimension. It is a different matter that this is not a stable confinement, because any small perturbation called interchange perturbation gives rise to disruption of the plasma confinement or disturbance or destabilization of plasma confinement. But certainly one possibility is like this, that you can confine the plasma by using magnetic field such that the lines of force converge towards the end of the machine and plasma is filled in here. Then one can think of a confinement by using closed lines of force, and that is called toroidal confinement. The toroidal confinement is like this. Suppose I take a current carrying wire of very large length, then the lines of force around the wire are circular, they close on themselves. And if you can create a plasma somewhere here in this region, suppose I create a plasma in this region, so the plasma, if I can create in this region, one would expect that the particles in this region, because they are moving along the field lines and they will be gyrating about the field lines and may be confined. But what we had seen, that in such a situation, because the lines of force have a curvature, RC was in the outward direction, and they also have a inhomogeneity in the magnetic field, and that gives rise to drifts. The electrons move in one direction and ions in the other direction, perpendicular to the plane of this board by the V cross B force, and that produces a vertical electric field perpendicular to the plane of the board. So what really happens is that the electrons undergo a force, a drift, which is given as F cross Bs, upon E Bs square, and this drift is zeroth order drift, and this force is primarily the centrifugal force, which is m V parallel square upon radius of curvature Rc of the line of force where the particle is located, and that is in the radial direction Rc. So, what really happens here is that under this force, this negative sign here, that if magnetic field is in this case is in the z direction, suppose I choose a magnetic field in the z direction like this, not magnetic field is in the toroidal direction, Bs in this case is parallel to phi direction. The current that produces this magnetic field is in the z direction. In that case, this is in the phi direction, this force is in the radial direction. So, Rc radial cross phi is in the z direction, this is minus z direction. So, electron drift is parallel to minus z cap and ion drift is parallel to z cap. So, a very simple configuration that you have a current carrying conductor in the z direction perpendicular to the plane of this board, it will produce magnetic field, a circular line or closed lines of force, but this will produce a drift of electrons in the minus z direction and ion drift in the opposite direction. So, there will be a charge separation created between these two if you do not compensate for it, and that charge separation will produce an electric field Ez, and this electric field will give rise to E cross B drift of electrons and ions both in the same direction, and that turns out to be in the radial outward direction, and plasma confinement is not possible. So, though there is a good possibility that if you can compensate for these drifts, you can have particle confinement in the closed lines of force. However, this is a very serious challenge to compensate for these drifts of electrons and ions caused by curvature drift and grad B drift. Grad B drift is in the same direction as curvature drift, it just adds to it. So, this is a serious matter. What was really found in 1950s, late 50s, was a theorist in Soviet Union, that if you can have a current in the plasma in the azimuthal direction, the phi direction, the same direction in which a DC magnetic field, azimuthal magnetic field is produced by this current carrying wire, then there is a possibility to compensate for, to negate these drifts, and that is a very important contribution. We shall look into this in detail either today or in our next lecture, but that is a very important contribution to plasma physics, that just by passing a current in the system in the azimuthal direction, just in the plasma, have a current in the same direction in which the magnetic field exists in this direction, have a current in the plasma, then you can have this. This device will produce a toroidal plasma, and a more effective or more economic way of producing such a magnetic field is not to have a single wire along z direction, rather a configuration that has come up is like this, that you have a torus. Torus is like this. So, close this on itself. Close this curve on this self like this and this one. This is a torus like a bicycle tube, which if you straighten will be a cylinder, and if you bend the cylinder it will bend on itself to form a torus. So, plasma is filled in this here, and by using magnetic field coils which go like this schematically, you will produce a magnetic field in this direction. This is the direction of static magnetic field called B phi, and you do not require a conductor passing through the center of the torus. Rather, these field coils are very close to the plasma, to this region where you want to create a plasma, they can produce a magnetic field more effectively. So, and if you can treat this entire torus as a secondary of a transformer, it should be possible to induce a current also. So, current is also you can create here in the same direction, and let me call as I phi, plasma current, that can produce a suitable magnetic field that can neutralize the drifts caused by grad B drift and centrifugal force or curvature drift. So, this is the kind of more economic configuration for toroidal confinement, and this device is known as Tokamak. And this is at the forefront of fusion research. However, let me, before I delve into Tokamak, let me also talk to you about the other scheme of fusion, which is called inertial confinement fusion. In this scheme, one considers a pellet, a spherical pellet of deuterium tritium, and you shine laser light from all directions. Usually 16 beams, laser beams are employed. They are launched from 16 different directions onto a deuterium tritium pellet, whose radius could be of the order of a centimeter. And it is a deuterium tritium mixture where if you calculate the atomic density of deuterium and tritium, then that will be typically of the order of 10 to the power 22 atoms per centimeter cube. So, if you convert this deuterium tritium, when the laser arrives here, it converts this deuterium tritium mixture, and this radius of this from here to here is typically, I call this as R0, is around a centimeter. Then a hot plasma is created here, and as soon as the plasma is created, this density is more than the critical density for this laser. Suppose the laser frequency is omega, then the plasma frequency that it produces is around 5 into 10 to the power 15 radian per second, and if it is a few times 10 to 22, then this will be slightly more. Sorry, this is omega p. The frequency of the laser that you employ here either have 0.8 micron wavelength, they are called TI sapphire laser, or 1.06 micron wavelength called neodymium glass laser. So, typically the wavelength is around 1 micron. So, if I take 1 micron here, then omega turns out to be typically 2 into 10 to the power 15 radian per second. Obviously, this omega is less than omega p, so the laser will not penetrate once the plasma is created. And once the plasma is created, it will deposit its energy only on the surface, and surface will expand. So, when the surface expands, you have a lower density outer region called corona. And this happens within a fraction of a picosecond. So, once the laser arrives here, it quickly converts the plasma this into a plasma, and a hot outer region is called corona is produced. Well, the physics of this process we shall discuss in detail later, but it would suffice us to say here that the hot plasma which is the plasma which is created outside, it will be, part of it will be transparent to the laser and part of it will not be transparent to the laser, because there will be some layer here at which the laser frequency equals, this is a layer, some sort of a layer here, at which omega p is equal to omega. Inside this, omega p is bigger than omega, the laser frequency, and hence that is a overdense plasma as far as laser is concerned. So, laser will penetrate up to the critical layer. And it will deposit its energy, so this gets heated. But you get a situation in which the outer region is very hot and hence pressure is very large, whereas the inner region is relatively cold, and there is a sharp pressure gradient created near the critical layer, and that will launch a shock wave inward and compress the core. So, suppose the core has been compressed to a radius r0 prime. This is the core which in the process of compression will get heated, and where you expect thermonuclear fusion reactions to take place. Suppose you can confine this plasma where the density has also increased. When you compress the core, the density which was initially so much will increase. Let me initial density, let me denote by symbol N0. The new density I will call as N0, N. So, the modified density and the confinement time of the compressed core, this should exceed 10 to the power 14 per centimeter cube into second to achieve for the Lawson criteria. This is what you require. So, this is the density of the compressed core, and this is the confinement time of the compressed core, because compressed core, after this compressed, it will start expanding because it has been heated. And typical confinement time you can estimate by considering the process to be ambipolar diffusion process or ambipolar expansion. Let me explain what is ambipolar expansion. Suppose I have a core of deuterium tritium heated. If I assume the electrons and ions are at comparable temperatures, so if Te is comparable to Ti, still thermal velocity of electrons is much bigger than thermal velocity of ions due to their different masses. So, what will happen? The plasma which is filled in here have electrons moving with large thermal velocity, so those electrons will quickly get out. They will come out here. However, when they come out, there is a net positive charge left behind, and that pulls these electrons back. So, the net positive charge is left out in the inside, and that pulls these electrons back and does not allow the electrons to leave a distance more than a Debye length. But this positive charge will repel the ions themselves, and consequently ions will move out. So, once ion can go out to a larger distance, suppose ions can come out to this region, this distance, then the electrons can go further out, they can move little more, and in this way the electrons and ions as a assembly moves with charge separation of the order of Debye length, which is quite small. So, this is called ambipolar diffusion and ambipolar or ambipolar expansion. In which the ions and electrons move together and the velocity with which this happens, it turns out to be of the order of Cs, called sound velocity, and which is equal to electron temperature upon ion mass. If the plasma is a mixture of deuterium and tritium, then this ion mass is some sort of a geometric mean or some mean of tritium and deuterium masses. So, this is the kind of speed one gets, and if the initial radius of the plasma is suppose r0 dash, then the time of confinement would be of the order of the radius of the compressed core divided by Cs. Please note that the original radius of the pellet that we considered was around a centimeter. This compressed radius will be only a few millimeter. Sound velocity, if you calculate at a temperature of about few keV, then this will be of the order of few times 10 to 7 centimeter, or maybe close to 10 to 8 centimeter per second. So, this is typically of the order of a nanosecond. So, if it is like a nanosecond or a few nanosecond, then the density that you would require should be certainly more than 10 to 23 or so to achieve Lawson criterion. It means this compression is mandatory, but there is a beauty in there that in the Lawson criteria n tau product that is of our interest, which I want to be more than 10 to the power 14 per centimeter cube into second. This, if the size decreases of the pellet, then this will increase as 1 upon radius of the pellet to the power 3, inversely to it varies inversely with the radius. So, if the radius becomes half, the density will become 8 times. If it becomes 1/3, it becomes 27 times larger, whereas the confinement time scale says r0 dash by Cs. So, r0 dash means when you take the product, this scale says 1 upon r dash square, means compression is certainly helpful to achieve this, and one can achieve when people have achieved this product, but obviously you require this to be satisfied in conjunction with electron temperature also to exceed 10 keV. So, this condition has to be satisfied in conjunction with electron temperature of this order. Well, this scheme we shall discuss separately in one of the lectures of inertial confinement fusion. It has made tremendous progress over the years, and I think I will return to this in a separate lecture. Today I would like to take you back to toroidal confinement, and let me discuss some basic features of toroidal confinement, and then we shall return to more details in our next lecture. So, a primary thing in toroidal confinement is to counter the grade B and curvature drifts, and for that people thought let us a plasma. So, the Tokamak, if I have a schematic of a Tokamak like this, where plasma is, this is the axis of the system, axis of symmetry perpendicular to the plane of the board, which I call as z axis, and let me call this as my x direction, this is my y direction, and we use a right handed coordinate system. So, what you will have, that I am having a plasma which has a toroidal magnetic field B phi, and it also has a toroidal current I phi. I phi is not uniform. I do not know what kind of variation I phi I should have to have a optimum confinement. But what I expect is that this toroidal, this azimuthal current I phi will produce magnetic field, and the lines of force will be perpendicular to this direction. If I draw a plane perpendicular to phi direction, suppose I draw a plane like this, then the lines of force will be circles about this phi direction, phi cap. So, I am expecting, just like in case of a wire which was carrying current like this, the lines of force were circles. Here also I am expecting the lines of force to be circles about these bent lines of force. There should be circles in a plane perpendicular to this. If I draw a plane perpendicular to phi direction, then the lines of force will be like this. So, this is my phi direction, normal to the plane of this board, then these will be the lines of force. I will call this magnetic field as BP, toroidal magnetic field. So, there are two kinds of magnetic field in the system. One is a magnetic field produced by the external coils like these. These are the coils that will produce a magnetic field B phi, and a current in the phi direction will produce a magnetic field that I call BP. I would like to discuss a constant of motion, and that will give you us a clue of plasma confinement. Just like in a mirror machine, I introduced a quantity called magnetic moment. Here also I would like to introduce a similar quantity. Let me write down the magnetic field in the plasma as P is equal to B phi phi cap. This is the toroidal magnetic field produced by external currents coil, plus the magnetic field produced by the plasma current, which I call as BP, also called toroidal magnetic field. Now, as magnetic field can always be expressed as curl of a vector potential, I can write down BP also as curl of a vector potential I will call as AP. The direction of AP is in the direction of plasma current. If I am taking the plasma current in the phi direction, then I expect this AP to be also in the phi direction. So, AP I will choose as AP and phi cap. For an axis symmetric system, and this is the approximation we always make for Tokamak. So, axis symmetric system is the one, axis symmetric, for which all the quantities like current, magnetic field, they do not depend on phi. Means all points inside the Tokamak have the same likelihood of having same value of magnetic field here, here, here. So, magnitude of these quantities do not change with phi. So, choose delta delta phi equal to 0. Now, in this case I would like to write down the azimuthal equation of motion. Azimuthal equation of motion, which is 1 upon r d dt of m r square phi dot is equal to the force on the electron due to the magnetic field, which is B cross B force. And I must write down the phi component of this. Now, this is the minus E is the charge of the electron. If I write down the components, this will be Vz and Br minus Vr Bz. Br and Bz are both the components of magnetic field Bp, because the toroidal magnetic field is in the phi direction, and we are not interested in that component. We are interested in the radial and z components of B field, so which are deducible from curl of AP. So, let me write down the radial and z component of magnetic field. So, Bp we have as curl of AP, and Bp radial would be how much? We simply call as Br, radial component of Bp is Br, and this will be equal to R. If I write down, I must write down a phi component here, Z here, minus Z here, and phi there. So, this turns out to minus delta delta Z of AP based on the phi direction, and Bz that I need will be equal to radial component of this operating over the phi component, turns out to be equal to 1 upon R delta delta R of R A P. AP is A phi. So, these are the two components. If I substitute these two in the equation of azimuthal motion, I get 1 upon R. Well, sometimes people denote this small r, sometimes we call as capital R. We are writing as capital R is simply the variable coordinate or major radius coordinate. So, this is d dt of m r square phi dot is equal to minus E V z B r. Now, V z I write down as say d z by dt. This is my V z into B r, which is this quantity. So, minus delta delta z of A p. Then I term minus V r, which I write down as d r by dt. This is for V r multiplied by B z, which is this term. So, it becomes 1 upon R delta delta R of R A P. This is what I get. What I can do here, I can multiply this equation by R and divide by R. I can write down, please, this R and capital R are no different. So, let me use the same symbol here, put a capital R here rather than a small r. So, if I do this and take a small r common, I can take this is equal to, and minus time also common, it becomes E upon capital R, and then this can be rewritten as delta delta Z of R A P into dz by dt plus this term, which is delta delta R of R A P into dr by dt. Here R I have taken inside the delta delta Z operator, because R is independent variable, independent of Z. So, I have taken this inside. You may treat this as a full derivative of RAP with respect to time, because if AP does not depend on time explicitly, it depends only on R and phi, R and Z, and there is no phi dependence. So, this entire quantity can be written as E upon R into ddt of RAP, and if you look at the left hand side and right hand side, 1 upon R is common in both of them, and consequently you get a constant of motion, and which I would like to write down. The constant of motion turns out to be m r square phi dot minus E r a phi is a constant of motion. This is very important constant of motion, and it has tremendous implication for plasma confinement in a tokamak, just like magnetic moment has implication for plasma confinement in a mirror machine. And I think implications of this we shall discuss in our next lecture. We are coming close to end for today's talk, and in the next talk we will discuss the implication of this on plasma confinement. Thank you very much.